Yeah, hello everyone. Welcome to our O1 Labs, o1js workshop. It will be more of a, I guess, quick talk, giving you a quick introduction. There won't be anything to follow along with like code or anything, so you don't need to like type in your computer. Just listen and we will do questions at the end. Awesome. And yeah, there's a cat over there. If you are a fan of cats, I like cats a lot, that's why I used it. So yeah, what do we actually do? Just giving a bit of background. O1 Labs is a blockchain company, that's why we are here, I guess. We have originally incubated Mina protocol, and we are still actively contributing to it. Our overall mission is we are dedicated to catalyzing a new generation of applications powered by zero-knowledge cryptography. So we do a couple of things. We have a couple products besides Mina. Number one being o1js, which is our TypeScript SDK for writing zero-knowledge proofs and ZK apps on Mina. And we also do other work. So for example, we are building a ZKVM for the Optimism ZK stack, proving the fault program. So if you're interested, check that out. In order to give a bit, I guess, like background, like what Mina is and like why o1js is a thing, let's just briefly talk about Mina. So Mina is a very light blockchain. It uses zero-knowledge proofs to sort of like prove the state of the blockchain rather than requiring all the transaction or the block data and just like rerunning it. That makes the entire thing like very scalable and very trustless because of, again, like rerunning the entire chain, you can simply prove a zero-knowledge proof, which is like very quickly. In addition to that, we do have something called ZK apps, which is our sort of like quote-unquote off-chain execution layer for like smart contracts, which enable you to do privacy-preserving applications on top of Mina. Just briefly comparing the execution models of like other chains and Mina. If you look at Ethereum, we know that there's like code on-chain, and a user sends a transaction describing their execution of a smart contract to the chain, and every node of the Ethereum network will then have to run that computation more or less. So that is a, I guess, what we call on-chain execution model. Looking at Mina, it's the exact opposite. What we do is we compute off-chain. The user computes a proof off-chain in their browser, or maybe Node.js, and simply sends a small proof with a list of state updates to the Mina blockchain, and the Mina blockchain only verifies the proof. So that gives us a couple of very cool benefits. The blockchain stays scalable through succinctness. We achieve user privacy through zero-knowledge, and we have unlimited execution and like off-chain computation that we can simply tap in on demand. You may wonder when this thing is like happening, I guess. So currently there's like test world mission 2.0 ongoing. It launched a couple of weeks ago. There's like regular calls to like hard fork on Discord. So we are currently in like testnet stages of this entire thing, and if you're interested, check out the Mina protocol, Twitter, and the Discord server, join the call, so if you're interested in the protocol itself. So the actual topic of the presentation is o1js, which is our TypeScript SDK, and it's a zero-knowledge framework, and it is TypeScript. We also like to call it general purpose embedded SDK. The reason for embedded SDK is because it's literally TypeScript, not a TypeScript-ish type of thing that you have to compile. It is a circuit-based approach, so it's not a ZKVM, but it's a circuit approach, which means you simply write your application's circuit in TypeScript. You can do sort of like two things with it. Thing number one being writing Mina smart contracts, ZK apps, but you can also write off-chain peer-to-peer zero-knowledge applications using recursion. And when I say it's TypeScript, I mean it's literally TypeScript. So it inherits a lot of ecosystem from the TypeScript and JavaScript community. There's a lot of developer tools that you can tap into. It is easily accessible to like Web2 developers because it's only TypeScript. There's like easy integration into like existing Web2 frameworks and like stacks and stuff like that. Just beginning plainly with like TypeScript, IDEs, VS Code, but also runtime environments like Node. You can use it on the front end with Vue, which is my favorite, and also tap into like NPM, which gives you like access to a lot of packages, a pre-built ecosystem and stuff like that. So like easy onboarding, easy integration. So o1js the core technology behind it actually has been around for a while, so it's already like battle tested, nothing that we sort of like cooked up on like a weekend hackathon, I guess, which doesn't mean it's a bad thing. But yeah, so Kimchi is our core proof system. It's a longish proof system that also powers our ZK VM for optimism. It supports a rich set of like custom gates, for example, like Poseidon, range checks, XOR rotation for on field, and more on that later. There's support for lookups, no trusted setup, of course. There's like all sorts of stuff in development. And last but not least, our infinite recursion protocol that actually powers Mina is called Pickles, and it has been in sort of like production mainnet since the launch of Mina, which was like 2 years ago. So, like I mentioned, o1js is a very rich standard library. You have access to custom gadgets, bitwise operations, comparisons, integer types. There's like Poseidon and native signatures for like more cryptography use cases. There will soon be ECDSA, SHA-3, lookups, and more. There's also all sorts of protocol features that I will talk about in a second. And there's another thing that I will talk about in a second. It's the ZK program, which is a very interesting abstraction for infinite recursive circuits. So yeah, and that allows you to build like peer-to-peer applications, which are executed in the browser, proven in the browser, and just sent to your friends or to the blockchain. So yeah, if you want to get started with o1js, if you're looking at it, if you're interested in it, you can simply install the ZK app CLI. It's a tool that we built to like let you bootstrap your application. You can choose a list of predefined UI frameworks that you want to work with, and it's a simple command. So there's like all sorts of things you can do with it, also deploy to the network, lets you create examples, gives you some debugging information. So that's definitely the go-to thing that I would recommend if you're interested in working with o1js. So yeah, let's look at the actual smart contract API that we have. If you go through the entire ZK app CLI, I guess like bootstrapping phase, this is an example contract that the ZK app CLI will give you. It's a simple addition contract, right? So you can see, I showed this earlier, it is simply TypeScript. You simply extend the smart contract API, which is given by o1js, and that enables you to like define your own business logic. There's a couple fields on this basic example. The state field, so on Mina blockchain, we can have some state on-chain. It is public state, and we can have up to 8 field elements. There's also other things that you can utilize to get access to more state, for example, Merkle trees that can reference off-chain state. Then there's the init method, which lets you initialize your contract with default state if needed. And then there's the actual important part of the application, which is which are methods. So methods are like any other smart contract methods. They let you execute some code, update the chain state, and in addition to traditional smart contracts, they also generate a proof. So the method keyword decorator is used to declare functions on a smart contract as provable methods. Here's important to mention that all the inputs into the method, here, for example, the X of type field, they are all private. So these are data types and inputs, they stay private on the user's machine in the browser. They do not become publicly visible when the transaction and the proof leaves your PC. You have access to on-chain state, you can query the on-chain state, you can get it, you can make assertions with it. You can then add to the on-chain state and finally set the on-chain state using the .set method on the object. So yeah, that's pretty much a very basic smart contract that you will have access to as soon as you spin up the ZK app CLI, go through the tutorials, and yeah, but there's more actually. There's something we call ZK program, which is a sort of like lightweight and powerful API sibling of smart contract. It allows you to write circuits directly without any, I guess, like protocol features, any auxiliary data types that you need, or like any access to like the Mina protocol itself. It also allows you to verify proofs recursively. So you can either build recursive chains like Mina, where you prove each block individually and then merge them, or you can build sort of like reducers, like MapReduce or like binary trees, and always verify 2 proofs at once. So that enables you to do all sorts of like peer-to-peer applications. And these proofs that you generate using the ZK program can also become private input to smart contracts, which is very powerful. And yeah, I mentioned it earlier, this is like a very powerful tool if you want to build peer-to-peer applications in your browser, or also in combination with smart contracts. So to give a better understanding of how this thing works, recursion, let's just simply look at Fibonacci sequences. I think everyone should know what it is, but just briefly going through the, I guess, idea of Fibonacci sequences. Oh, that was too quick. So it's essentially a sequence that follows a certain, I guess, like function definition. It's fn equals fn minus 1 plus fn minus 2. So what that means is we start with two numbers at the very beginning, f0 and f1, both equaling 1. There's also definitions where f0 is 0 and f1 is 1, but we just go with these start values for n greater than 1. And we simply apply the formula at the very top. And this allows us to like generate a sequence. So looking at the table below, that's just a quick example going from f0 to f5. We simply take always the previous two values and add them together to get the next one. Then we go one step ahead, take the previous two again and add them together, and we just keep doing that. So how can we actually fit that into like recursion? It's relatively simple. We actually have two cases. Number one being the base case, I guess, where we initialize the first two values, f1 and f0. We set them to 1 because that's how we defined it. And then there's a recursive case, fn. The recursive case has to do two things. It needs to verify the correctness of fn minus 1 and fn minus 2. And it also needs to calculate the new fn, which simply means adding the two numbers together. And then return the final value. So how does it look like? We can simply use the ZK program API to define a recursive proof. We add two methods to it, number one being the base case, where you simply spit out a 1 value and then proving the sequence, which is the recursive step, where we always take the previous two inputs and then go further and further, generate a new output, and continue doing so. So our base case is simply giving us the value number 1. And yeah, that's pretty easy. We simply return a field element that has the value 1. Going to the recursive case, we now need to verify the correctness of the previous elements, the previous two elements, and calculate the new one, and then simply return the value. So that works very straightforward. We have two private inputs. The private inputs being the proof of the previous iteration. We simply verify them, .verify, which literally verifies the previous proofs recursively. We add the two inputs together and we return them. So everything together gives us a very basic Fibonacci sequence recursion example. And we can simply call .compile to compile the ZK program. We can simply call .basecase or .proof sequence with the inputs, which simply generates a zero-knowledge proof of the inputs using the computation, and we can also very easily verify it directly in the browser or directly in your Node.js environment or any other runtime. So there's other cool protocol features that are more smart contract related that I still wanted to mention in case anyone is interested in using them. There's something called custom tokens, which are obviously tokens. They are native to the blockchain, so you can utilize them to build all sorts of like token-like behavior. There's something called actions and reducers, which help with concurrency and state interactions. So they are quite valuable. There's events. Events are simple. They are just like events in Solidity. There's permissions for smart contracts. There's time-locked accounts. So there's like all sorts of things. So you really have access to your full stack of, I guess, like features like you're used to with like Solidity or other applications. So there's now a quick outlook. There's a cat again. Some things we are working on. Gadgets. So we are currently actively working on gadgets, but what are they? They're essentially low-level building blocks, like hardware accelerators for like cryptography, for like math, and all sorts of stuff. And they are building on top of custom gates. So there's a couple of things we have just very recently finished. For example, all sorts of bitwise operations, bitwise gadgets, and XOR, shift, rotation, and not. And these allow you to build like foreign, I guess, cryptography algorithms like SHA-256 or SHA-3 and other algorithms very efficiently because they are sort of like low-level accelerators in the proof system. There's other exciting things we're working on, foreign fields, which are work in progress, which will allow us to do foreign field arithmetic, mainly multiplication, addition, and other algorithms. With foreign fields, we will have access to foreign elliptic curves, or rather elliptic curves that are based on foreign fields. And that will then eventually unlock very soon ECDSA verification and things like that. So that's a very, very powerful primitive. We are also very actively working on other improvements and performance. Chunking will be a big one that will massively increase the amount of constraints that can be proven. We just have recently finished prover and witness generation performance, which we have landed, but there's still more work to do. We have just recently finished implementing prover artifact caching, so you can compile your prover artifacts. There's folding coming, which we are working on, which will be a big and interesting feature, and more. So briefly going into like examples and use cases to give you a couple of interesting ideas. So private DAO in governments is a very important thing. You can build privacy-based voting applications, survey applications. There's like I guess an idea about safe interoperability between blockchains or like state channels. That is a very interesting one. Simply using recursive peer-to-peer proofs to verify computation between two parties or between blockchains. There's a DeFi and real-world data oracle case. You can prove data off-chain, you can verify it on-chain. There could be all sorts of like DeFi, real-world data use cases. There's an entire thing about ZK rollups and infrastructures which you can do. And there's also a big part about like anonymized proofs, KYC, identity, off-chain information. That's also a big one. I'm waiting a second so everyone can take a picture. That's like planned into the talk. It's a very big important thing. It took me a long time, by the way, like getting all these, yeah. So yeah, now we are talking about challenges. I actually originally thought challenges would already be announced, but I think they're being announced in the intro talk soon. We've set 5 challenges, starting with number 1, ZK Gaming. So the idea is for you to build a game, like a game mechanic using o1js, or maybe even some sort of like anti-cheat mechanism. A couple of examples are listed there, but you're not limited to these examples. We hope everyone is like creative. We are open to new ideas. Just giving you a couple of ideas. So there's like Hearthstone, card games like poker is like a big one, chess as well. Then ZK voting, like I mentioned previously, just simply build a voting application or a survey application using zero knowledge. You can use ZK for either scaling, either privacy. You can even prove the tallying of the votes. So there's a big thing there. There's a crypto primitive challenge, which sort of like is about building and implementing popular cryptographic primitives. For example, you can use the bitwise gadgets that I introduced earlier to implement SHA-256. But not limited to SHA-256. There's a zero-knowledge data structure challenge in which you can build things like Merkle mountain ranges, rate-limiting nullifiers, mutator sets, so like a lot of stuff. There's actually another one, which is a free-form sort of like thing. Just build whatever you think is interesting. And yeah, if you want to get all the information about the challenges, the bounties, take a look at their folio. I'm sure they will be introduced later at the intro presentation as well. And if you're interested, come to our booth. We will have like things, QR codes where you can learn more. So yeah, it is time to hack. Check out the QR code. It leads you to a Notion page where you can see all the challenges, the introduction, I guess, steps, how to get, where to find what, where are the community, and all these things. So yeah, you see. I think we have time for questions. If anyone wants to take pictures of the other cats, I can go back. So there's like no limitations.
Are there any non-cat related questions? Or cat related, actually, I don't mind.
Thanks, Florian. When the ECDSA stuff lands, will I be able to use Ethereum state in ZK apps?
So yeah, what you can do with ECDSA is verify Ethereum signatures. Another thing that people may be interested in is using Keychuck, like SHA-3, to verify Ethereum data structures. So for example, there could be some data on Ethereum. You could like build a Merkle proof of it using SHA-3 or like Keychuck or anything, verify it within a Mina proof, and then in combination with ECDSA, verify Ethereum signatures, look at the data in Ethereum transactions and stuff like that.
Could you go through a little bit more on like the flow of making one of these apps using TypeScript? So like, how much do I have to like commit like some state on the Mina blockchain before I have to actually run my website? Or
Yeah. So let me just go back to the very beginning to the example contract.
and the prompt for your cat pictures as well. That's great.
Yeah, okay, so let's say you want to start building a smart contract like this, a very basic add smart contract, which simply like takes an input, a private input, applies it to some on-chain state, and then commits the on-chain state back to Mina. So what you would do is you would go ahead, download the ZK app CLI, go through the prompts, the, I guess, like introduction, choose what framework you want to use, Vue, Nuxt, whatever we have available. And this will like spawn you with some like predefined contract. There's on-chain state. It's only limited to 8 field elements. So if you want to reference more on-chain state, you should tap into Merkle trees. We have tutorials on our docs. So there's like all sorts of tutorials on the docs, not only about Merkle trees, but also other stuff, very introductory tutorials, getting started, more advanced things. So you would start writing your smart contract. And depending on your, I guess, application, you can reference on-chain state. You may want to use Merkle trees to verify or like reference more off-chain state. You can then go ahead and construct transactions, which I didn't add in this talk, and then like simply send them to the blockchain, where they are like verified. You generate a proof of it, and yeah, I hope that answers your question.
Are there any limits or constraints when developing with the o1js SDK? Because as we know, like in Cairo or in Circom, you are limited to like additions or multiplications, and you have to split that, which is annoying. But like in the o1js SDK, is it possible to freely develop like the fullest as developers need?
Yes, and that's a very good question. So we provide you with all sorts of like standard library access. The most basic ones are obviously addition, multiplication. You have access to things like assertions, greater than, less than, assert equal. But you also have access to like more advanced primitives, like Poseidon hashing, Schnorr signatures, and all these things. And now also with custom gates and gadgets, you have access to bitwise operations and stuff like that. You can pull in other libraries that already have done some sort of like pre-work for you. You can use these if they're o1js compatible. So you're not limited to like only addition and multiplication. You have access to a very vast standard library which provides you with all sorts of computation, right? So essentially there's like, I guess like no limit to what you can do. You can do like any application that, or like any logic that you imagine. It is really just like writing TypeScript, right? So you're like not limited by only 2, I guess, primitives or 2 operations.
Also, like it's known that SHA-256 is pretty inefficient while like developing with ZK. Like in Circom, it used to be like 150,000 constraints. But like I'm wondering with o1js how efficient it is and what makes it efficient also.
Yeah. So I mentioned earlier that we implemented gadgets, and gadgets, they are like cryptographic accelerators within our ZK SDK. they are based on custom gates in our Plonkish proof system. And that simply means certain operations like NOT, XOR, shift, which you all need for SHA-256, they are like much quicker. They only need one constraint instead of like 1,000, right? So if you wanted to implement SHA-256, you simply go into these bitwise operations and or NOT, shift, whatever, and utilize them to build your algorithm, right? It wasn't possible previously to do it efficient, but now with custom gates and gadgets, you can do operations like that more efficiently without having to like add 1,000 constraints. So yeah.
Thanks.
Do you have the concept of like gas or anything like that? Like, can anyone just prove these things using my app? And how do I keep my keys and secure? Like, is that the same concept or is it a different analogy?
So we don't have gas because computation happens off-chain. You are essentially paying for your own computation by running the prover, the software in your browser, right? So there's like, you're not paying any node on-chain to do the computation for you. There is a transaction fee that you have to pay with every transaction that you're sending to the network, but it doesn't depend on the amount of computation that you can do. That's also why I said earlier that you can tap into unlimited amount of off-chain computation because you are doing the computation and not any on-chain node. You know, like on Ethereum, like you essentially have to pay the entire network to do the computation over and over and over again. With Mina, you do it yourself. You have a tiny proof, which is like, you know, very quickly, very efficiently to verify. You send it to the chain, they verify it, they say, yes, it's correct, or no, it's not correct. And yeah, so there's no notion of gas.
But would that mean that my app needs some sort of wallet integration?
Yeah, so if you want to interact with the Mina blockchain, you can do it directly in o1js. So there's like things that are provided to you, like transaction APIs, and you can also use wallet extensions.
Yeah, one quick question. Do you have any restrictions on the complexity of the circuit? Let's say, for example, if I have a circuit with more than 5,000 if else clause, would that be okay? Or it gonna be too slow or anything?
Yep. Yeah. So at the moment, we can prove 2 to the power of 16 constraints. I mentioned earlier that we are working on chunking, which has been implemented. We just need to expose it in o1js, which will allow you to prove 2 to the power of 32 constraints. So that is a lot.
Earlier, you mentioned accessing on-chain data in the smart contracts, but I saw that only the proofs are stored basically on-chain. So where is that data coming from, and how, like, when you access the data, how isn't gonna be out of date when you actually want to commit your proof or submit your transaction?
Yes. So every account on the Mina blockchain, including smart contract accounts, they have some on-chain state. It is 8 field elements. There are some other on-chain state, like permissions are stored, the verification key of your application is stored in order to verify your proof. But yeah, so there's something called actions and reducers, which I mentioned about earlier. Instead of directly changing the on-chain state, what you can do is dispatch an action which says increment A. Then another user is also doing the same, increment B, increment A by 5, whatever. They're sort of like dispatching instructions. And then later on, you can come in, invoke a different method and say, reduce all these transactions. Like go through them, apply them one by one. And that's how you can prevent sort of like race conditions and concurrency.
So what happens if my application needed you to have certain amount of whatever other token, but when I submit the transaction, you still have it, but in the meantime, someone, for some reason, your balance changed, and it's just going to revert, or? So
tokens are an interesting example because you don't implement tokens like you do with Solidity. It's not a map structure in a smart contract. Tokens are actually something that are natively implemented on the layer 1, right? So rather than having a smart contract that keeps track of all the balances in a map data structure, they're actually like baked into the blockchain, right? So there's not the same, I guess, like constraints with like smart contract state because it's differently handled. That makes sense.
Thanks.
Okay, thank you very much, Florian.
Thank you.
This was a great speech.